As we found out, a quantum computer is a device capable of solving problems that a classical computer cannot solve. Now let's understand why it gives a speed gain when solving some of these problems. To begin with, remember that in the classical computer, the basic unit of information is a classical bit. It can take two values, 0 or 1. The simplest implementation of a bit that each of you would have encountered is a switch. A switch can be either on or off and has no other provisions. In a quantum computer, a qubit is used as a unit of information. A qubit is a quantum system that has two basis states. Unlike a classical bit, a quantum bit can take other values, not just either 0 or 1. A qubit, like any quantum object, can be in superposition of its basis states. This means that the state of the qubit is set by the psi wave function shown on the slide. In this regard, the qubit is more like a volume knob, which can be not only in position 0, with the sound turned off altogether, or in position 1, when the sound has maximum volume, but also is any intermediate position. Unlike the classical bit, the state of which can be easily measured and recognized, in the quantum case we cannot know the state of psi by measurement. From quantum mechanics, it follows that through measurement we can only learn limited information about the quantum states. When we measure a qubit, we get state 0's probability a squared, or state 1 with probability b squared. Since the coefficients are probabilities, the probability to measure a qubit in any state is set by 1, and it is equal to a squared plus b squared. It is convenient to use a geometric representation to describe a qubit. Considering the superposition property and the fact that a modulo squared plus b modulo squared is equal to 1, we can rewrite the expression for the state of the qubit in the form shown on the slide. Here, all angles are real numbers. These angles define a point of the 3D unit sphere, as shown in the figure. This sphere is called the Bloch sphere. It allows you to visualize the state of a single qubit and often helps you understand the ideas underlying certain quantum computer algorithms. In addition, many operations on simple qubit are elegantly described using the Bloch sphere. However, it should be understood that the possibility for such a representation are limited, since today there is no known simple generalization of the Bloch sphere to the case of n qubits. The presence of superposition properties in the quantum world makes a quantum computer a powerful device. If we have n qubits in a quantum computer, then, due to the superposition property, they can simultaneously be in 2 to the power of n states. In a classical computer, n qubits are always in one state. As a result, when performing quantum transformation on qubits, we can simultaneously change 2 to the power of n states instead of 1. This allows quantum parallelism in computing and the ability to solve some problems much faster. Although a qubit's superposition property might seem strange or unlikely even, its existence has been proven experimentally many times. For the practical implementation of qubits, quantum mechanical systems are used that have only two basic states. For example, this can be projections of the electron spin, the direction of the nuclear spin in a uniform magnetic field, two linear or circular polarization of photons, two states of an electron in a single atom, as well as others.